Okay, good afternoon. And the topic of today's lecture is numerical scheme for the linear advection equation. So now last time we finished with the discussion of numerical methods for just one ordinary differential equation. And last time we just wrote the code. I explained to you how to do that and try to explain the main features of the numerical solution for the linear ordinary differential equation. And also we illustrated the main concepts, that is convergence, stability, and consistency. Now we move towards the partial differential equations, because linear ordinary differential equation is not enough, because we would like to solve gas dynamic equations, Euler equations. And as we discussed, the linear advection equation is apparently one of the simplest possible analog equation, simplified model for the Euler equations. And so this is the reminder of the second lecture. At the second lecture, I explained how so are these equations the simplified models for the Euler equation. We not derived, but so I explained to you why would we analyze these simplified models. So this is nonlinear scalar conservation law, written in conservation form and quasi-linear form. And we discussed the main properties of this equation, the properties of the solutions, defined the characteristics of this scalar conservation law, discussed that they are straight lines, and we discussed what is the expansion wave, what is the compression wave, the mechanism of the formation of shock waves in this model. And if we take f of u as lambda u, where lambda is constant, either greater than 0 or less than 0, so then we obtain the linear advection equation. And we are going to discuss today the numerical methods for this just one scalar linear advection equation. So that's the goal of today's lecture. And again, for this linear advection equation, we discussed how the characteristic lines should look like. So I'd like to remind you that the exact solution for this linear advection equation looks like this one: psi of x minus lambda t, where psi is the initial data. It's very important because within the scope of this lecture, we are going to compare our numerical results with the exact solution. That is why we should understand how the exact solution looks like. So the name, linear advection equation, that's because the exact solution of this equation is the advection of the initial profile with the speed of lambda in the positive direction of x-axis if lambda is greater than 0. So if lambda is negative, then it propagates to the left. So this is just to check that indeed this u exact is the exact solution. We can just take the derivative with respect to x, with respect to t, and so be sure that this is the exact solution of our problem indeed. Very important for us today to understand what is the characteristic line for this model. So according to the exact solution, the initial conditions propagate at a constant speed lambda to the right for lambda greater than 0 and to the left for lambda less than 0. This is the simplest possible example of a wave solution. So the lines x minus lambda t equals constant are called wavefronts. So because if x minus lambda t equals constant, it means that u exact for this x and t is also constant. So it means that the profile propagates along this characteristic line. So this is x-axis, t-axis, and like we consider 3 time instance: t1, t2, and t3. And so this red dotted line, dashed line, correspond to the solution, and so it illustrates that the exact solution propagates along this characteristic line. Or we can take the derivative for both sides of this equation and get that u is constant for dx over dt equals lambda. So the wavefronts dx over dt equals lambda are called characteristics, curves, or simply characteristics. We have already discussed all these things. So now the first maybe issue is that, this was for initial value problem. So we didn't have any boundaries here, but if we move towards some real simulations, in real simulations we always have boundaries. And that is why we also have the problem of setting of boundary conditions, and later we'll discuss it as well. But now, even for just linear advection equation, that's the meaningful issue. So what does it mean? So suppose we are going to solve our equation not for the whole axis x from minus infinity to plus infinity, but we want to solve it on interval from 0 to 1 here. And the question is, how many boundary conditions do we need for that? So it looks like, if you are not aware of properties of these equations, you can think that you need to impose one boundary condition to the left boundary and one condition to the right one. But actually that's not true here, because so consider, for example, this point, the red point. The solution of this point is determined, so we put the characteristic emit from this point. It intersects our x-axis in this point, and according to the properties of our linear advection equation, it means that the solution here at this point is equal to the solution at this point. So it means that we should know the solution at each of this point of the interval from 0 to 1 on the x-axis. So this interval corresponds to the initial solution. So we should know, so we need the initial solution. This is phi function here in this example. But at the same time, consider this point, and also emit the characteristic line, and it will intersect not the x-axis but t-axis here. So it means that if we solve the linear advection equation with lambda equals constant greater than 0, we need also to impose the boundary condition at the left boundary, because the solution is the propagation of this profile to the positive direction of x-axis. And at the same time, we do not need the boundary condition here at all. So the equations, the solution of this equation itself demands only one boundary condition at left boundary. So if the lambda would be less than 0, then we need only one boundary condition to the right boundary. That's maybe not obvious for everybody, that actually not always you need to impose boundary conditions for both boundaries. Especially it may be difficult if you're a computational guy, and for sure in the software or in your computation you need to impose boundary conditions at all boundaries. But this is the technical issue. So for sure your numerical method requires the boundary conditions at all boundaries. But it does not need. It does not mean that your equations itself they need conditions at all the boundaries, and that's very important. For example, this is also the model situation for much more complex situation when we are going to solve Euler equations. And for Euler equations, the flows can be subsonic, can be supersonic, and depending on the velocity of the flow at the boundary, we also need different number of boundary conditions, and that's much more complex issue. And this is the simplest explanation. Why is it so? Because of the nature of the solution and the mechanism of propagation of waves in this model. That's not directly about the numerical methods, but it's very important feature and issue that also affects all simulations, so numerical solution of hyperbolic models. Some historical background. So the last lecture I explained to you the approach, how can we estimate the accuracy of our numerical method if we do not know the exact solution. And the approach was based on so-called Richardson extrapolation, when we compute the numerical solution on 3 different computational meshes, and we can compare the errors between the first, the second, and third meshes, and we can extract from this comparison the accuracy order of our method. Actually, Richardson is believed to be the founding father of CFD. It is believed that in 1906, Richardson formulated a numerical method to calculate where channels should be dug to drain marsh. And this was successful, and he started work on a new project to compute the stresses in a Mansfield dam. So he computed the stresses in this complex technical object. This project was large enough that he is required the effort of a team. So actually he solved the Poisson equation. And he was the first who decided that to solve the Poisson equation, he can substitute the real derivatives with the finite differences. But for that, he needed to do some computations. And he organized a team of small boys who were good in arithmetic and paid them 1 penny for every 10 correct calculations. The boys were called computers. Maybe after that, so the term computer appeared. This was the first time that the principles of mass production had been applied to a mathematical calculation. Actually, this story, this historical background, you can find it in a number of books on CFD, but actually I heard it in this lecture of Philip Rowe. Actually, he also used this term, colorful fluid dynamics, and he explained that. So, yes, nowadays, very often the CFD is associated with some beautiful pictures, but we should nevertheless understand the basics of the process of computation. And so, what was the idea? As I told, he solved the Poisson equation, and he suggested to substitute the derivative, x derivative, here using central difference. We have already discussed. What does it mean, central difference? And if we need to approximate the second derivative, then we can use this 3-point stencil. And even in 2D, we can approximate this operator using stencil that comprises 5 points, 5-point stencil, and actually that was the idea. And it is also known that so maybe apparently the first time when people met the problems with the stability also is about his work. Actually. So he realized that such methods, finite different methods, were the only way to deal with complex equations and irregular geometry, because no analytics for some real objects. And he began to consider the possibility of weather forecasting by numerical process. So he would like to forecast weather. And he carried out trial calculations while serving an ambulance driver during the First World War. So he was at the First World War, but he was not a soldier. He was an ambulance driver because he was against, weapons war. The most interesting thing is follows. So the mathematical model, so the equations that he would like to solve were correct. So the model for the weather forecasting was great. But to forecast, we need some initial data. For example, the speed of wind or temperature distribution or something like that. And actually, such set of data was available. So Richardson has available detailed atmospheric data of a region of Germany on the morning of a particular day. So someday all the necessary information for his model was available, and he would like to predict the parameters, for example, for tomorrow, and fed it into his formulas. His forecast predicted winds of over 100 miles per hour, but the actual day had been calm and so no wind at all. So the equations were correct, and the initial data was correct, but numerical predictions were totally wrong. He made no errors in his physics or mathematics or in his arithmetic, but something still went wrong. And the problem is that he used unstable numerical method. So we have already discussed what does it mean unstable. So it means that some small errors in computations, they provides the blow up of your numerical solution. So actually it can be illustrated for simple equation of heat conductivity, because actually from numerical point of view, his model so is equivalent to just one heat conductivity equation. So it is known that for this equation, if you use this numerical stencil, so you use the explicit derivative in time and this central derivative for the second derivative with respect to x. So this numerical scheme is stable if the time step is small enough. But he used this stencil, and so he used these 3 points for the approximation of derivative in time, and the 3 points, these points for the approximation of derivative in space. And actually it is known that this numerical scheme is totally unstable. That is why he carried out a number of steps and got totally wrong result, because this numerical scheme cannot be used. So that's the point. Interesting historical fact. Okay, now let's move towards our main topic. When we consider just one linear ordinary differential equation, we started with the formulation of simplest possible numerical method. That was just an explicit order scheme. So let's do the same thing here. So we would like to solve our du over dt plus lambda d over dx equals 0 equation. And let's start with the substitution of our derivative with respect to time d over dt with this just explicit order scheme. And also we use this also explicit formula for numerical approximation for du over dx. So we will use this xt space. So m is special index, and n is time index, and the dot mn. So it means that we analyze the numerical solution at the point with special coordinate xn for the time level tn. And suppose that we have the uniform computational grid. So the distance between each nodes in x direction is h, and suppose we have the constant time step tau. So the distance between these tn and tn plus 1 is tau, and so umn is the grid function, and so the special index will be in subscript, and the time index will be superscript. So umn means the grid function at this point, umn. And so the set of points in this xt space that I used to compute the value at the next time level is called a stencil. So for this scheme, the stencil, we have three point stencil, this one, and this one. And it is also called a left angle stencil, because so they form an angle with the left orientation, right? Actually, as for ordinary differential equation, we can propose a lot of different ways how to compute, how to approximate the derivative with respect to time and with respect to x. But this is apparently the simplest possible one, and actually the best one, in fact, for if you consider first order schemes. So this scheme is called Courant-Isaacson-Rees scheme, or CIR for short. It was proposed in 1952. Let's analyze the properties of this scheme. We did not formulate the mathematically strict definitions for convergence, stability, and consistency in this case. Actually, it can be done in just as for ordinary differential equation, although there are some differences, and I'd like to do it next time. But now, at this moment, so we can do it just by analogy. So just as for ordinary differential equation, to check the consistency. So if this numerical approximation is consistent with our initial problem, we should put the exact solution into our scheme, and this way we will get the truncation error. And then we should analyze the truncation error. If the truncation error goes to 0 when h and tau goes to 0, it means that the numerical scheme is consistent with our problem. But now we have two small parameters. So we believe that h is small enough, so its parameters that is significantly less than 1. And so tau is also a very small parameter. So let's check the consistency. So consistency analysis of a finite difference scheme. So delta f is a truncation error, just for one step. And now, so here u is grid function, and here u is the solution of our differential equation. And we substitute our grid function with the solution of our equation. So n plus 1 means u of xn tn plus 1. Okay, and then we use the standard approach. We use Taylor series expansions. So, but now we have expansion in x and in t. So yes, and you should choose any suitable node, and we will carry out the so the Taylor series expansion should be carried out for any node. For example, let's take xmtn here. And so uxmtn plus 1 means u. For further consideration, we can just omit the arguments of our function. So if we will write just u, it means u at point xmtn. U sub t, tau, the second derivative with respect to time, t squared over t factorial, big O of t cubic. So this is Taylor series expansion for this point. Then we need also Taylor series expansion for this point. But now all the derivatives will be with respect to x, because this is the our function computed in this node that is shifted from this one in x direction. So it's u minus ux, h minus because we use this point for Taylor series expansion. This is minus h. Plus the second derivative with respect to x, h squared over 2 factorial plus big O of h to the third power. And now we should place this guy here and this here. So I just formally replaced uxmtn plus 1 with Taylor series expansion, and also here. And we can see that this u and this u they cancel out, and this u and this u they also cancel out, and we divide so the numerator over tau and get u tau plus utt t over 2 from this, and big O of t squared, then lambda ux minus, so the next term, big O of h squared. Then we use the typical trick. U is the solution of our initial differential problem. It means that ut plus lambda ux equals 0, because we solved this equation, ut plus lambda ux equals 0, and we believe that u is the solution of this problem. And so we still have utt tau over 2 minus lambda uxx h over 2, and also some terms proportional to time to tau squared, h squared, and so on. And the main, the main term of the truncation error is proportional to tau and h to 1. So that is why CIR is a first-order accurate upwind scheme, both in time and space. So now we should characterize the accuracy of our formula in time and in space. And actually, the accuracy orders can be different. But actually, in fact, we try to keep the same because actually x and t, so both directions, we should pay the same attention to both of them. What does that mean, upwind? So here we can also discuss the next very important concept of upwinding. So upwind means so if we have some flow So you should understand that the space that downstream. It means that if you have flow from left to right, so in those directions we have downstream or downflow, and at that side upstream or upwind. So upwind scheme means that for the approximation of derivative with respect to x, we use dots from the region where we have already known our solution, where we know our solution. So the solution of this linear direction equation for lambda greater than 0 is the propagation of wavefront from left to right. It means that when we compute the value here, we should know the solution here. And it means that, and so for the numerical approximation of our derivative, we should take this point, not this one, for example. So if we take this point or this, it means that we use the upwinding. So we use the points from upstream, not from downstream. And usually, so when you, if you solve some problem and you need to provide some approximation, so you should and you solve the hyperbolic problem, so the problem with wave propagation, you always should follow the idea of upstreaming, because usually it will provide you the stable approximations. In contrast to taking points to downstream. Okay, so many words can be said about this, simplest possible scheme, but actually all of them are very important. So we checked the consistency of this numerical approximation and discussed the constant of upwinding. We know that consistency is not enough, and actually you can use this numerical scheme for the solution of linear direction equation, but only if some stability conditions is valid. And it means that there should be some relationship between tau and h. So you are not able to take, so suppose we have some computational grid. So it's given to us. And the time step and the special step h is given. So the question usually is what time step tau should we take to be able to compute our solution, because we are not able to take arbitrarily big time step. Why? Why is it so? Explanation using characteristic line, CFL stability condition. What's the idea? Let's analyze and give the interpretation of our scheme using characteristic line. So consider this point n+1. So we want to compute the solution here, right? Let's emit the characteristic line from this point, and it will intersect the nth time layer at some point P. Suppose this point P will be between this node Mn and this node m-1n. And suppose, so it divides the segment between the points m-1n and mn at the nth time layer in the following proportion: x1 and x2. So we can rewrite our scheme right in the following manner. So we just express um and n+1, and also so put all the rest terms to the right hand side. And then we should multiply both sides to tau, and we'll get the parameter sigma lambda tau over h. So this parameter is very, very important. So it's called Courant number. So it's the ratio. It's the ratio lambda tau and h. And this parameter is always defines the stability properties of our numerical method. Why is it so? So this is the characteristic line, dx over dt equals lambda. So what does it mean? It means the tangent of this angle, this one, is equal to lambda, right? So it means that tangent of this angle on one hand is lambda, on the other hand it's xt over tau, right? So xt over tau is lambda, because this is the characteristic line, dx over dt equals lambda. Then we can express xt. x2. So x2 equals lambda tau, but lambda tau is sigma h. So it's sigma h, and so x1 is h minus sigma h. So it's 1 minus sigma h. What does it mean from geometrical point of view? So what is the characteristic line? Characteristics is a line along which our solution propagates without changing. It means that the solution here at this point is equal to the solution at this point, at the point P. But the problem is that we do not know the solution at this point. We know the solution here and here. So we are not able to, so we do not know the solution on any arbitrary point at the nth time layer. We know the solution only in specific points. But we know the solution here and here, and we need to know the solution here. Let's just interpolate to find the solution here between these 2 points. And so, in fact, this formula can be interpreted as just the interpolation between the values here and here with the weights proportional to or just equal to x1 and x2. So the characteristic line divides the segment onto 2 parts, and we should interpolate to find this value, take into account these values x1 and x2. So actually the same scheme, Courant-Isaacson-Rees numerical scheme, can be considered as just interpolation at the nth time layer. Okay, but the problem is that actually maybe the characteristic line will intersect our nth time layer, not here, but for example here or here. Is it possible? So it's possible, but if we have such situation, there is so-called CFL stability condition or Courant-Friedrichs-Levy condition. So if the characteristic line will intersect our nth time layer here, it means that the scheme will not be stable. So it's forbidden. If your parameters lambda, tau, and h so as for characteristic line will intersect the time layer nth somewhere here, you will not be able to use these parameters in simulations. Your numerical scheme will be unstable. So what does it mean, CFL stability condition? So the domain of dependence of the differential equation. So there is a concept of domain of dependence of the differential equation. So it means that which points at the nth time layer, they affect our solution. In fact, for our linear direction equation, it's just one point P, because the solution point P is equal to the solution at this point. So P is just the domain of dependence of the differential equation. So the domain of dependence of the differential equation should be entirely contained in the numerical domain of dependence of the discretized equation. So this point P should be inside the domain of dependence for our numerical method. And the domain of dependence for our numerical method, all the points on the nth time layer. So that is why, so the point P should be inside this segment for the CFL stability conditions to be valid. So the Courant-Isaacson-Rees scheme is stable if P lies between m-1n and mn. What does it mean from this current number point of view? So if this point P between 2 points, it means that current number should be between 0 and 1. So it should be between 0 and 1. Then this point will be between this m-1 and m. Otherwise, for example, if you'll take sigma equals 1.5, it will intersect it here at the center of this segment, and so on. What does it mean? Sigma should be between 0 and 1. Once again, suppose that we know, so we built the computational grid. For example, we took h equal 0.01. And the equation, and we would like to solve the linear direction equation with lambda equals 1. So we are given by some equation. Somebody asked us to solve this equation and told us that he would like to get the result on this computational grid to get, exact enough results. The question is, what time step should we take? So from this consideration, time step should be sigma h over lambda. So it means that, so it should be proportional to sigma. So your time step cannot be just arbitrarily. It should be like h over lambda is the time for your propagation. So it's the time necessary for your propagation. Is the time necessary for your wave to propagate the length of one computational mesh, and this coefficient sigma. Okay, so this is the condition. So it means some limitation on the value of your time step. So time step could not be large, very large. It is limited with this current number constant. So that's the interpretation of the Courant-Isaacson-Rees from a characteristic analysis point of view, and also the stability condition. Okay. So all these considerations were for lambda greater than 0. But what if lambda is less than 0? Because if you will try later to expand this, so these results to the nonlinear case, the problem is that for the nonlinear case you have here, for example, u or some f of u, and it can be negative or positive. So anyway, we should understand what will happen if lambda is less than 0. For example, this picture when we discussed the necessary number of boundary conditions, and I told you that if lambda is less than 0, then you need initial condition and boundary condition on another boundary. And what does it mean for our numerical scheme? So if lambda is greater than 0, then our stencil should be left angle. But if lambda is less than 0, then the characteristic line will look like this one. And it means that this point is not between these 2 points. So it means that for lambda less than 0, we are not able to use the same numerical scheme. It will be unstable. We have just discussed it. And for that, we should use another numerical scheme. So we should just change this. So actually, this is the same numerical scheme, but we take into account the sign of lambda. And this is the right angle. So we should use this point and this point for numerical approximation of our derivative. And so the scheme will look like this one. So the time approximation will be the same, but for approximation of the derivative with respect to x, it will be plus 1n minus umn. So it's possible to show that this scheme has the same first accuracy order in time and space, and it's also stable if this point is between this one and this one, so all the same. But if lambda is less than 0, you should take right angle, not the left one. Now, let's try to generalize these two schemes for arbitrary sign of lambda. So we know the scheme for lambda greater than 0, and we know the scheme for lambda less than 0, right? So actually, this is the same scheme, but actually on different grid stencil. It's possible to generalize these two schemes into one in the following manner. You can check it. So suppose we have just one notation for both schemes. Now it means now we have this big stencil, four-point stencil. And you can check that this formula is the generalization for these two. So the idea is the usage of mod sigma, the absolute value of sigma. So if, for example, sigma is greater than 0 and sigma is lambda tau over h, it means that lambda greater than 0, then mod sigma equals sigma, and then this term and this term, they cancel out, and so you can check that you will get this formula exactly. So if sigma is negative, then mod sigma equals minus sigma, and so this term and this term will cancel out, and you will get this formula. It is known that if we just skip this term, this scheme corresponds to the unstable scheme with a central difference. So we discussed that for what does it mean, central difference, right? So this is the approximation of our first derivative using plus 1 and minus 1. We used this approximation when we discussed ordinary differential equation. And actually for ordinary differential equation, that was okay. But the problem was, we discussed it previously on our previous lecture, we need to choose the correct value of u1, right? So if it's not accurate enough, your numerical solution will, oscillate. It will be stable, but not good. But if we use this central difference approximation for advection equation, you're not able to use this scheme at all. But this term can be considered as the correction of unstable scheme with a central difference. So this makes the scheme stable. But actually, this is not very important to us. Just to, just for you to know that these two formulas can be generalized in the following manner. Much more important for us, another way how can we generalize these two formulas into one. Let's introduce some object called f m plus 1/2 m. So f is numerical flux. So this is much more interesting for us. So we can generalize them in the following manner. So f equals 1/2 of these terms, and again, the main idea is that we use mod lambda. So if lambda is greater than 0, this numerical flux equals umn or um plus 1n if lambda is less than 0. And again, you can check. You can check that if lambda is greater than 0, you will get this formula or this formula. Actually, here is just arithmetic. So we just check carefully and realize that indeed this formula and this, so they're just the same. But now there are very important outcomes of this generalization, namely, so up to this moment we had, so we considered only nodes, and we had our numerical, our grid function defined in these nodes, um minus 1, um plus 1. But now we introduced another concept, f. And so f is the numerical flux. And numerical flux has indices with 1/2. So it means that numerical flux refers to not the center, so not to node, but some point between nodes. And so we introduce the concept of cells, computational cells. And our grid function is defined in the center of cell. And we have numerical fluxes through the boundary between cells. So for sure, cell is something three-dimensional, right? So these terms, flux, surface, so cell, so they comes from 3D. So in 3D we have computational cell, for example, cubic, or so more complex shape computational cell, and this cell has edges, and so. But this is the simplification in 1D. So in 1D we have cells and boundaries or edges or surfaces between the cells and numerical fluxes. We could obtain this notation if we would if we would consider our linear advection equation not in primitive variables, not in quasi-linear form, but in conservation form. So d over dt plus lambda du over dx equals to 0. We can put lambda in brackets and introduce flux, right? du over dt plus df over dx equals 0. And then we say that, okay, we will approximate time. So du over dt using explicit order scheme. And we will approximate the term with fluxes somehow. We do not know how. So we use this approximation. And the idea that, so this scheme is called finite volume scheme. So the scheme that is written as a conservation, as a numerical approximation of conservation law is called a finite difference. So it means that this notation means that the change in during one time step, the value here, so our grid function here, is due to numerical flux through the right edge of our computational cell and the left one. And the modern point of view for numerical methods for Euler equations or for hyperbolic equations is that almost all, so the majority of numerical methods can be written in this form. And all the differences between the methods will be in how can we compute this numerical flux. So this numerical flux corresponds to Courant-Isaacson-Rees scheme. But actually, I will show you that other numerical schemes can also be written in this form. And the only difference will be in the formula for numerical flux. So I'm writing here. So how can we compute this numerical flux? Here is just the example for Courant-Isaacson-Rees numerical scheme. Why do we discuss these finite volume schemes? Schemes that ensure the fulfillment of discrete analogs of conservation laws are called conservative. So the most beauty, so the most favorable property of this finite volume scheme is that it's conservative. It means that if we'll summarize the changes of parameters in these cells for one time step, so this numerical flux is right for this cell and left for this one. This numerical flux is flux through the right boundary for this cell and through the left boundary for this one. And you can see this minus. It means that when we summarize all these formulas for all computational cells, the fluxes, the same flux for neighboring cells will cancel out. And so you will get that the in total the conservation is valid. So it means that your U is conservative. So you will get that the only changing of this U is due to flux through the left boundary of your computational domain and the right boundary of your computational domain. And so actually, okay, I will finish and we'll have a break. We discussed that the most important properties of the numerical method is the convergence, the stability, the consistency. That is not enough. For example, on previous lecture, we got, you can check that when we use central difference scheme, our numerical solution was non-monotonic. So our exact solution was a decreasing function, and our numerical solution was non-monotonic. So for example, the property of monotonicity is very important, or the property of conservation. So if you solve some physical problem, for example, if you want to compute the flow in some I don't know, pipe or in some domain, so one of the most important for you, if you want to get some physically relevant results, that for you, so you still you solve the equations, so mass conservation, momentum conservation, energy conservation, and you should be it's necessary for these quantities to be conserved. So, for example, you must be sure that you don't have some additional mass or loss of your mass in your computational domain. So maybe you can make some mistakes, maybe some features of your flow may be wrong, maybe your scheme is not very accurate, but you should be sure that the discrete analogs of conservation laws are valid. And so that's a very important property. So okay, we started with the simplest possible scheme for linear advection equation, Courant-Isaacson-Rees numerical scheme. Discussed the properties for lambda greater than 0, the consistency, the stability, CFL stability criterion. Then we considered also the case lambda is less than 0, and then we generalized these two schemes for arbitrary sign of lambda, and we carried out it in the form of so-called finite volume scheme, right? So the next lecture will be about, I will explain how this numerical scheme for one scalar conservation law, for linear advection equation, can be also formulated for, first of all, system of linear equations of hyperbolic type, and then can be used for the solution of nonlinear system of partial differential equations of the hyperbolic type. So actually, all these concepts that we're discussing now, they're very important, and they can be used later for much more complex objects. But the idea is just the same. So one more time. Within the scope of our course, we will formulate all the numerical methods for the solution of Euler equations. So they will be the finite volume methods. In this approach, we have computational cell, and our numerical scheme is written as a balanced law for this computational cell. So the changing of qualities in this cell. So for gas dynamics, it will be density, momentum, and energy is due to fluxes through the boundaries of our computational cell. And the problem is how to compute this numerical flux, right? And so this finite volume formulation differs from finite differences, because in finite differences we just approximated our derivatives, so in time and in space, and that's it. But here we do not approximate the derivative of our function. Instead, we work with flux to get the numerical flux. Okay, so this was for Courant-Isaacson-Rees numerical scheme, but this is the first order scheme. And as for ordinary differential equation, we want to be able to use more accurate numerical scheme, because here again, so the lower order numerical scheme are usually not used for real simulations. So let's build one of the most known second order numerical scheme. We'll begin with an unstable scheme with a central difference. So I've told you that. So this numerical scheme is unstable. So it means that you can try to write a program and to compute the advection of your wavefront using this numerical scheme, and you will see that it doesn't work. It will not work. Because this central difference is not compatible with explicit time integration. But let's correct this bad numerical scheme, this unstable numerical scheme. For that, we also must check the consistency, first of all, numerical scheme. So psi here is the same as delta f on previous slide. So this is the truncation error. So again, we use Taylor series expansion for this n plus 1 here. It's Taylor series expansion in time, minus u and u and u, they will cancel out. And we also use Taylor series expansion for this term and for this term, but in x, because m is spatial index and n is time index. And if you insert all these Taylor series expansions here, here also u and uxx and uxx, so a lot of terms will cancel out. And finally, you get ut plus lambda ux, and again, these two terms in sum equals 0, because here u is the solution of our differential problem. And here we have only this term, the main term of truncation error, utt t over 2. So in fact, this but this is for bad scheme, for unstable scheme. So the main term of truncation error is proportional to tau. Let's approximate this term as well and subtract for Fermat numerical scheme. So let's do the following steps. We will use the consequences of our equation. So we solve this equation: ut equals minus lambda ux, right? Then we can take derivative in t and in x. So if we'll actually, I have this on another slide. I will show you. It is yeah, it's here. So we solve this equation: ut plus lambda ux equals 0. Then we can take derivative with respect to t. So utt plus lambda uxt equals 0, and with respect to x, utx plus lambda uxx equals 0, right? And then for continuous functions, utx equals uxt. So you can express it here and put it here, and then you will get utt equals lambda squared uxx. Actually, this is wave equation. So in fact, our linear direction equation is equivalent to wave propagation equation. But this is the second order equation, this is the first order equation. But utt equals lambda squared uxx, it follows just from our initial equation. We can do the same procedure one more time. It will be necessary for us, and on this way you will get utt equals minus lambda squared uxxx and so on. So there are consequences of our initial problem. But here we need this one: utt equals lambda squared uxx. utt equals lambda squared uxx. And now we substitute it here. And so the leading term of the truncation error is lambda squared over 2 uxx tau. And now let's approximate this uxx using central difference scheme. This one. So this is approximation for uxx and subtract it from our bad scheme. So we had the unstable scheme with the central difference and the accuracy was tau h squared. Then we subtract the main term, the leading term of the truncation error, and now get big O of tau squared h squared, because we cancel out the term proportional to tau to 1. So this scheme is called Lax-Wendroff scheme, and this scheme is second accuracy order in both in time and space. And this scheme is stable again if the sigma is less than 1/2. So if so, you can think that your current number is less than some constant. So this is very typical limitation for explicit scheme for hyperbolic problems. And so these are some, from historical perspective, all these schemes were obtained by their authors from different considerations, like, okay, let's approximate this derivative using this approach, these derivatives using that approach, and so on. But as I told, almost all, schemes that I use in practice can be written in the finite volume approach. So just like for Courant-Isaacson-Rees scheme, this scheme can be rewritten in this formula. So here is flux not from 2 arguments but from 1, and this argument should be computed using this formula. So the Lax-Wendroff scheme also can be computed in the form of finite volume method. The most interesting thing, what the results will be. So now let's compare the numerical solutions for Courant-Isaacson-Rees numerical scheme and Lax-Wendroff numerical scheme. So we can take different types of our initial data, of our psi function. So if psi function is very smooth, almost all numerical schemes will work excellent, and the higher order of your numerical scheme, so the more accurate your numerical scheme, the best result will be. If your initial data is very smooth. But you will have problems if your initial solution is not smooth. So this is a very typical case called a square wave. So if you have discontinuities in your initial data, why do we consider this square wave? Because again, this is a simplified model for order equations, and we discussed that in hyperbolic models, in conservation laws, the situation when you even if you do not have this discontinuity initially, you can have this discontinuity during your numerical simulation. So there are mechanisms in the model for the formation of shock waves, gradient catastrophe, and it happened that actually the most problems occur. So you have problems when you try to compute the discontinuous solutions. That is why we need to test our schemes when considering test with this square wave. So consider Courant-Isaacson-Rees scheme. So suppose we solve the equation du over dt plus du over dx. So lambda equals 1. So h 0.01. And usually the simulations for this linear direction equation are carried out using some constant value for current number. So suppose sigma equals 0.5. So once again, sigma is lambda tau over h. So lambda is fixed, h we have chosen some value. It means that sigma equals 0.5 determines our time step. So the sigma determines our time step. And the CFL condition was, I can remind you that sigma should be between 0 and 1. So this value is okay. So so our numerical scheme should be stable. And so we consider the computational. So the computational domain is an interval from 0 to 2. And so initially our square wave was here for x equals to 0.5. And we compute 50 steps, 100 steps, and 150 steps. using Courant-Isaacson-Rees numerical scheme. What can we see? Well, we can see that we do not have our discontinuities anymore, right? So initially, the profile was with discontinuity, but our numerical scheme smears these sharp discontinuities. Actually, we have some, very diffusive profile. This is the first feature. The second feature is that in time, so the amplitude of our wave, of our signal becomes smaller and smaller and smaller. And suppose, for example, that so all these numerical schemes were developed mostly because of atomic project and space exploration. For example, we need to compute the propagation of shock wave from atomic explosion of atomic bomb on the surface of our Earth, and we use this scheme. So it means that after 150 steps, you will lose about 20% of the amplitude of your wave, right? That's not acceptable. So that's the illustration why first-order schemes usually are not good and not enough for simulations. So your profile becomes more smeared, and you lose your amplitude. So these are bad things. But on the other hand, if you are not interested in absolute values, for example, you explore some process and you need in principle understand what's going on, your solution is actually physically relevant. So you have some rising part and falling part, and actually in your numerical simulation you also have some rising part and falling part, and actually the numerical solution is not too bad if we look on some just physics of the process. So this is for first order scheme, and this is for the second order scheme, Lax-Wendroff scheme. Again, so we take the same linear direction equation, the same h, the same sigma parameter. It's also okay. So the numerical scheme is stable. So this is not so it's stable numerical scheme, and we can see totally different picture, right? So first of all, our numerical profile is much more localized, and it's still localized for after 100 steps, after 150 steps. It's not smearing, and you can see that the amplitude, some average amplitude, also is still near 1. But the problem is the solution overshoots and undershoots by about 20%. So that's also not good, because for example, here we can maybe we can overestimate some process, but for example, if it's I don't know, density or something like that, we can get negative pressures or densities or whatever. So that's bad. That's also unphysical. So when you have very small amplitude, that's bad. But if you have overshooting, and so overshooting is not so bad as it is. But the problem is that you have these oscillations. So these spurious oscillations. So your profile should have increasing part and decreasing part, and that's it. And you have decreasing, increasing, decreasing, and so on. So the numerical scheme provided you with a number of unphysical maximal and minimums, right? As one explanation, the Lax-Wendroff method has insufficient artificial viscosity, which leads to instability and spurious oscillations. So numerical. So we do not discuss the artificial viscosity, but when people tried to carry out first shock capture and simulations in 1950s, the idea was how to compute the shock wave. We should add numerical viscosity to our envisaged model. That is why, so its result can be interpreted as that Lax-Wendroff method has insufficient artificial viscosity. On the positive side, the solution is apparently properly located, and thus the overall phase error is slight. So it means that, so indeed, this shock wave is at the correct position. So that's a good point. It's localized, the shock wave is a good position, but you have spurious oscillations. So this slide and this slide, so this and this, they illustrate the main difficulty and what do people do in this area, in the area of numerical methods for hyperbolic equations. It can be summarized here. So so let's take more accurate computation on grid. just for illustration. So this is the first order scheme, this is the second order scheme. So for first order scheme, we do not have non-physical oscillations, that's a good point. But discontinuities are smeared and peak amplitudes fall with time. So that's bad points. For the second order scheme, we have non-physical oscillations and that's bad. But discontinuities are localized, peak amplitudes are preserved over time, and the location of shocks is, so they're correct. And so these are good points. And the question is it possible somehow to, I don't know, to mix, right, to combine these methods or these approaches to have only good points from both approaches, do not have negative features of these methods. And we will discuss how to do that. So, well, so I took these results from Lenny book, and I even didn't change. Actually, I could recompute it, but so that's very illustrative. There are a number of issues from theory point of view, from theoretical point of view. So he considered two test cases. It's just Lax-Wendroff scheme, just the same scheme as I have shown you previously. So this one, Lax-Wendroff scheme. He considered very, so not detailed computational grid with 40 nodes. So this interval was from -1 to 1, and he used periodic boundary condition. It means that your solution leaves your computational domain here at the right boundary and enters in the same form from the left. So it's periodic boundary condition. And he checked different resolution. So here n equals 40, and here n equals 600, and he checked different times. So, for example, 4, maybe several times your wavefront propagated from left to right, and 40. So many times. And he compared the numerical results. So increasing the number of grid points improves the solution in some way, but makes it worse in other way. So the problem is that when you have discontinuous solutions, the increase in the number of grid points does not necessarily improve your numerical solution, and that's very bad. And it's very difficult to understand, because we expect that, for example, just for ordinary differential equation, for linear ordinary differential equation, that we can take, we can refine our computational mesh by a factor of 2, and we can expect that the result, at least maybe the error will not decrease by a factor of 2, but anyway, the solution should be better, because we took more accurate computational grid. But here, what can we say? This is a very rough computational mesh, and you have some overshooting of about 1.05, and this is the same time instant F4, but for more accurate computational grid, and you have great overshooting. So you took the more accurate computational grid, and you have bigger error, and so that's bad. And it means that actually classical definitions of convergence, stability, and consistency, and more important, Lax equivalent theorem, they are not valid for non-smooth solution. So in particular, increasing the number of grid points creates large ringing oscillations to the left of jump discontinuities. It means that this one. So for not accurate enough computational grid, you do not have these, oscillations, but here you have them. Increasing the final time also increases the ringing oscillations. So this is for t equals 4, and this is for t equals 40. You can see that. So you even get bigger oscillation. So you also should take into account time, because you can compute very long, and the behavior becomes bad. So once again, not everywhere, because but it also becomes more smooth here. For example, this is a shock wave, not shock, but just discontinuity, and this is for early time instant, and this for later time instant. So it becomes more smooth, but at the same time, the amplitude of your pulsations become bigger. As an often overlooked point for most numerical methods, the truncation error. Maybe truncation error is not very accurate term here. Just error does not go to 0 in the presence of jump discontinuities. In other words, most numerical approximations are not consistent for non-smooth solutions. So then the Lax equivalent theorem, we discussed it. So the previous lecture, before previous, only applies to smooth solutions. Linear stability and convergence are distinct for non-smooth solutions. So it means that for non-smooth solutions, we should introduce another concept of stability, nonlinear stability, so-called TVD conditions, so on. We will discuss it later. The Lax-Wendroff method is linearly stable when applied to linear advection equation. But one more time, if we will consider not a square wave, but some very smooth profile, we will not have these problems. So for smooth profiles, you can take high-order accurate numerical methods and obtain good results. Then, as expected by the Lax-Euler theorem, the Lax-Wendroff method converges to the true solution as delta x goes to 0 and delta t goes to 0 for smooth solutions. However, for solutions with jump discontinuities, the Lax-Wendroff method does not converge. For example, in the linear advection of often overlooked square wave, oscillations originating in the jump discontinuity spread slowly as time increases. Right, it's in here, we discussed it. So that's very, I think that's very important to show that some only general understanding of this Lax equivalent theorem is not enough if we are going to solve gas dynamics, where the formation of shock waves, especially in supersonic regimes, or maybe some other problems. So so today's the fifth lecture. I still didn't introduce the definition of hyperbolic system of equations. Actually, so all that we are discussing is about hyperbolic problems, hyperbolic equations, and that's not only gas dynamics. So there are a lot of different hyperbolic models. For example, the motion of blood in in our body. So also hyperbolic models, two-phase models, swirl equation. So many other models, and so the system of equations is hyperbolic. So all this is valid. Okay, so we discussed the Courant-Isaacson-Rees numerical scheme, Lax-Wendroff scheme, and on an example of these two schemes, I tried to explain to you the pros and cons of first-order schemes, so second-order schemes, and difficulties, especially in theory. Consider another scheme, so-called Lax scheme. So they're not just some schemes, so they are the most famous, the most important, and the most illustrative schemes. That is why I'm explaining you them. So Lax scheme, again, we use the explicit order scheme for time integration, and so this is central difference scheme. So this scheme does not work. So it's bad scheme, unstable scheme. But then we change one term. So we use not umn here, but 1/2 of um-1n, um plus 1n. So it means that we just omit the point xmtn from our stencil, and now we have only 3-point stencil: umn plus 1, um plus 1n, and this one. Once again, why is it so? So it was just an idea of the author, right? So you can propose different methods, and within previous tens of years, only so the best schemes were used by people, and so this scheme was developed in 1950s, and at that time that was super great. So because this scheme generalized to gas dynamic equations, it was used to simulate the propagation of waves, I think, so the propagation of waves after explosion of atomic bomb was computed using this scheme. So you will see that the numerical results are not so good. But in principle, it's possible to obtain them. More accurate, less accurate, with some oscillations. So this scheme was actually one of the best and the first scheme that was used for real practical simulations. So we can check the consistency in the same manner. So we can use Taylor series expansion for this term, and for this term. So this is Taylor series expansion for in time for umn plus 1, right? And so all for the rest terms. This is the result. And because we put here, so previously, right, we did not mix the terms with n plus 1 and n plus 1 minus 1. That is why we obtained here some unusual terms. For example, this term, ux over t, h squared over 2. So there is some mix, some blend between tau and h. And the Lax scheme is an example of so-called conditionally consistent numerical scheme. So it means that it is consistent with the initial problem only if there is some relationship between tau and h. It means that if tau and h are the same order of smallest, so are the same order, then our truncation error is like big O of tau h, where sigma is lambda tau over h. So if tau an order of h, it means that this is the first order scheme. But if tau is an order of h squared, then the last scheme approximates not the initial equation, but the equation with the this term. So it's a sort of Berger's equation, but with constant lambda. So it's just maybe not too important, but just know that there could be some unusual cases when you explore the consistency of your numerical method. And actually, usually the simulations of linear advection equation are carried out with constant Courant number. It means that tau is an order of magnitude of h, and so usually this case is valid. It means that usually the Lax scheme is first order scheme both in space and time. Okay. Yeah. The numerical solution is not so good, so we can compute this square wave, and you can see that it's like we have such steps here and on the same steps on other side of your step, and when then they will meet, you have some ringing pulsations. So actually, yes, it can reproduce the numerical solution, can reproduce the exact one, but actually the result is not so good. In comparison with, for example, Courant-Isaacson-Rees numerical scheme. So the Courant-Isaacson-Rees numerical result is much better. So you can see 150 steps, the same problem, and you can see that amplitude is about 0.7, right? And here we had 0.9, not 9, but something. Yeah, even more than 0.9. So even among another important thing that even among different first order schemes, some schemes are more accurate. So it does not mean that if you have first order numerical method, all are bad or all are the same. No. So this is actually this is the best first order scheme, the most accurate. And this is not the most accurate, moreover, with some these features. But as I told, at the time when it was developed, it was super great, even this scheme. Okay. The following question is, we have Courant-Isaacson-Rees numerical scheme, we have Lax-Wendroff numerical scheme, we have Lax numerical scheme. Is it possible to somehow, so as for different signs of lambda, we generalized our Courant-Isaacson-Rees numerical scheme, right? Is it possible to generalize somehow how all the schemes for the solution of linear advection equation? Because we have first order, second order, schemes with oscillations, schemes without oscillations. Is it possible to provide some general point of view on all these topics? And there are different ways how to do that. So one is to use finite volume formulation. So and on this way we will use this approach at the next lecture. So on this way we can try to use the finite volume notation for all of these numerical schemes and try to find the most accurate finite volume numerical scheme. But we can propose another approach. So consider the Courant-Isaacson-Rees numerical scheme, right? For example, for lambda greater than 0. We can rewrite it, right? So when we studied the stability, we just expressed n plus 1, and so this is sigma minus 1 and 1 minus sigma. So interpolation between these two values at the nth time layer, right? Let's introduce the coefficient alpha minus 1, 0 and alpha 0, 0. When minus 1, because this we have minus 1. It's the index of shifting of our node with respect to node mn. So no shifting in time, that is y 0, and shifting in space, that is y minus 1. And here is alpha 0, 0, because this is coefficient for umn. No shifting regarding mn. So alpha, they are not constants, but they are constants in the sense that they depend only on sigma, not of our u function. Consider the Lax-Wendroff scheme. So this is Lax-Wendroff scheme. Again, this is an unstable scheme with central difference minus approximation of leading term of the truncation error. So this is a second order accurate scheme, big O of tau squared h squared. We can again express n plus 1. So the rest terms are in the right hand side. And again, we have minus 1, umn plus 1n. And some coefficients in front of them. And here is alpha minus 1, 0, because it's minus 1, alpha 0, 0, and alpha 1, 0. And they are all dependent on sigma. But here, because of this scheme is the second order, so this alpha are proportional to sigma to 2. And we can take the Lax scheme, right, where we also started with the central difference scheme, unstable, and change this term using this, 1/2 of this minus 1 n and um plus 1 n. And again, if we will express n plus 1, we will get another coefficient. So it's just two terms, but again, two coefficients, but so some other coefficients. And the idea is it possible to consider the grid stencil that is common for all these numerical schemes and try to build all possible numerical schemes for linear advection equation that will contain Courant-Isaacson-Rees, Lax-Wendroff, Lax scheme, and other schemes. How to do that? So the idea is very close to the idea of method of undetermined coefficients that we discussed 2 lectures ago, I think. So consider this stencil, grid stencil. So this grid stencil is common for Courant-Isaacson-Rees scheme, for Lax scheme, for Lax-Wendroff scheme. So all the schemes that we have discussed can be we can write it for this stencil. And so for linear advection equation, consider the family of schemes that can be written on this stencil using coefficients alpha mu nu, where alpha mu nu, they can be functions of tau h or sigma, because sigma is lambda tau over h, and we do not know them. But the thing is, yes, and the point mu 0 and mu1 is this point. We want to compute the solution here. Actually, we can consider implicit stencil and so on, but now, okay, it should be just explicit one. We have points only here, at the nth time layer. And the question is, what schemes can be built on this way? So we know just 3, but actually, obviously, we can propose many other schemes. How can we do that? Okay, let's try to solve this problem. How can we build, all schemes on this stencil? How can we generalize our knowledge about Courant-Isaacson-Rees scheme, Lax-Wendroff scheme or Lax scheme? For that, we should do just the same thing. Let's carry out the consistency analysis. So umn plus 1, all these terms with coefficients, alpha minus 2, alpha minus 1, and so on. And then we use Taylor series expansion for this guy, for this, and for this. We should keep the large number of terms because we want to get more accurate computational mesh. But this is the n plus 1 for this. And so this is the Taylor series in T. And all this for X, Taylor series in X. We take into account that this is this x m minus 2, it is y minus 2h, minus 2h, minus 2h, and so on. And then we should, put them here. We should put them here, just formal, so we substituted 4 to 7 into 3. So I used the numbers of these formulas for you to follow easier. And then again, like in the method of, so this is also the same method of undetermined coefficients. We should consider u u. So u to the left side and u to the right side. ut, and here we have ux. And here we also should, so I have already shown to you this slide. So here we should substitute derivatives in time using derivative in x to have, you know, the same terms. And collect all terms containing ut and ux on the left hand side, and group together all terms containing uxx, and uxxx in the right hand side. So we tried to organize our linear direction equation here, and the rest terms are in the right hand side. So ut plus something ux, but we need to approximate our linear direction equation, ut plus lambda ux. That is why this combination should be equal to lambda. Then we have, like in method of undetermined coefficients previously, we have a term that is not proportional to any small parameters. It's not proportional to h or tau or something like that. That is why it should equals 0. And then we have terms proportional to different degree of tau or h. So this is the local truncation error of the order of tau h. This is local truncation error of the order of tau squared h squared, and so on. But we have how many unknown coefficients? So we have 1, 2, 3, 4. So we have 4 unknown coefficients. It means that we are not able to take infinitely large number of these conditions. So we can take 1, 2, 3, 4. So 4 equations for our 4 unknowns, and the maximum possible accuracy of our numerical method is third one. So on this way, using 5 grid stencil, we can build numerical scheme of the accuracy 3 in time and in space. Okay, so now we should solve these equations for alpha and define different family of our schemes. It's very useful and convenient to use geometrical interpretation for this process. Actually, this is very simple, and I just keep all this mathematics because I want to show you the main mechanical result. I mean the result, the correspondence between all these numerical schemes. So we have 4 coefficients. We can take, for example, this one and this one as 3 coefficients, and we can express the rest two equations from this one and this one. So the red box and blue box, if we say that it should be equal to lambda because we approximate our equation, and this should be equal to 0 because it's not proportional to h and t. So in this case, we will get first order numerical scheme. So we can choose 2 coefficients, for example, alpha minus 2 and alpha 0 as 3 parameters. Then we can define the rest 2 coefficients from these 2 equations. It means that in space alpha minus 2, alpha 0, each point corresponds to some numerical scheme. We just take this point, they correspond to 2 values, alpha minus 2 and alpha 0, 0. We can express the rest 2, and we obtain some first order numerical scheme, right? For example, this point alpha, what is the point 0, 0? It means alpha minus 2, 0 and alpha 0, 0, 0. Alpha minus 2, 0, we don't have this term, and alpha 0, 0, 0, we don't have this term. So this is a scheme when we have only um minus 1 and um plus 1. This is this one. This is the Lax scheme. So this is a scheme when we had only um minus 1 and um plus 1, right? So in this general consideration, this scheme is the Lax scheme, and this is scheme 0, 1 minus sigma, and this scheme is Courant-Isaacson-Rees numerical scheme. So in this space we have a number of schemes that we know. For example, this is a Lax scheme, and this is Courant-Isaacson-Rees numerical scheme. What else can we plot here? We can plot here the region, the area, where all the coefficients are non-negative, where alpha minus 2, 0 is greater than 0, when alpha 0 is greater than 0, and these coefficients also greater than 0. And in this way, we will obtain A1, A2, A3, A4. So this is quadrilateral region where all the coefficients are non-negative. And this is very important for the discussion of these spurious oscillations because this is definition of so-called monotone schemes. So a scheme, this one, is said to be monotone if all the coefficients are not less than 0. So monotone schemes are schemes that are not less than 0. Why do we need monotone scheme? Because in linear case is just the same as a scheme is called monotonicity preserving if it we have the same monotonicity of our numerical profile with a numerical solution. So it means that if umn less than um plus 1 n for all m, at the next time step we have the same monotonicity. It means that we will do not have these spurious oscillations. So what's the problem with this numerical solution? With this numerical solution, right? The exact solution should decrease here and increase here. And we have a lot of decrease and increasing paths. It means that during numerical solution, our numerical scheme changed the monotonicity of our numerical profile. That is why we should have some theory for schemes that preserve monotonicity, because this bad behavior of numerical scheme can be formalized as non-monotonicity of numerical scheme. And monotonicity of the numerical scheme, at least for this linear directional equation, means that all the coefficients of our numerical scheme should be non-negative. So if in our numerical scheme all the coefficients will be non-negative, then it will be monotonicity preserving. So it's possible to prove that these two definitions are, just equivalent for the linear case. So it was done in this paper of Godunov. So it's very, very famous paper. Actually, it was published in Russian, and later it was translated. But anyway, the main results are known and explained, in many books. And there's very interesting history regarding this paper. So this paper actually changed the world of computations because very important concepts were introduced there. But the problem is that Godunov was unable to publish it for many years, because at that time this paper was on the boundary between physics and mathematics and computations. And when he submitted this paper to physical journals, he was rejected with the comment that this paper is not about physics. Then he submitted it to the mathematical journals, and he rejected because with the comment that it's not about mathematics, it's about physics. Because at that time there were no journals about computational physics at all. So, and this is a story how one of the best game-changing papers he was unable to publish it. And this mathematical sbornik is. It's even in Soviet Union, in Russia, it's not very known journal, and only his scientific advisor at that time he published not very legal maybe this paper, and only after that the world, after several years more, because it was published in Russian, knew these results. And once again, at that time it was very important, because it was a question how to compute any shock wave or anything. And in this paper he built so-called Godunov scheme, and also he published after that a lot of information about the process, how he do that. And he wrote, Godunov, that at the time when he worked on his work, he did not know about this Lax scheme. So it was published at that time, but he just didn't know about that. And he told that if he would know about the existence of Lax scheme, he would not do anything more, because the Lax scheme was enough for him to do the necessary computations. But he did not know about that. That is why he invented his own scheme. And his own scheme happened to be more accurate and better than Lax scheme. So this very interesting story. So in this space, we can plot all the schemes that are monotone. So they're here. So here the best first order schemes that can be used in real computations, such as Lax scheme and also Courant-Isaacson-Rees numerical scheme. And let's finalize. We can also add the next condition from consistency and plot the second order scheme. And in this space, the second order scheme is this line, this green line. And this green line does not intersect this quadrilateral. And this is the essence of Godunov theorem, that it's not possible to build a monotone scheme with an accuracy order greater than 1. And if we add one more condition of consistency, we can get this just 1 point. So on this 5 grid point, it's possible to build only one third order scheme, both in time and in space. And in this picture, I also have shown you one more time that this is Lax scheme, this is Courant-Isaacson-Rees scheme, and this is Lax-Wendroff scheme. So you can check, so indeed, that the coordinates of this point of intersection of this green line with this alpha 00 point axis corresponds to Lax-Wendroff scheme. So we provided some generalization of this linear schemes for linear advection equation in the space of undetermined coefficients, and also there are some features for future. For example, the Godunov theorem can be solved using this space of unknown coefficients. I think that yeah, so maybe this a bit confusing, all this mathematics, but I try to explain you the main idea. And so next time I'll show you the simulation results for. So I actually have already done that for Lax scheme, for Courant-Isaacson-Rees, for Lax-Wendroff. I will show you the simulation results, for example, for this point, and the specific the importance, for example, of this point and this point if you put the perpendicular here. So I will explain you a bit more about the properties of some numerical schemes that can be obtained from this consideration. But yeah, this is more about some theories. But anyway, I think the most important thing to understand relationships between different parts, because Lax invented her own scheme, those guys invented their own scheme, and if you do not have such general view, you may think it's about just separated research with no connecting to each other, but that's not true. So everything here is connected between each other. Okay, I think actually that's all, and so it's time to finish. Thank you everybody. So next time we'll continue with finite volume methods. So just continue this topic.